Okay, so in this one, I want to talk about uh, a little. I've already mentioned a little bit about this idea of initial values being a method by which we can go from pass from a general solution to a particular solution which meets certain specifications, which we might specify. And one form that those specifications can take are in initial values. Okay, initial value for initial values typically for both the function but also its derivatives, yeah, particularly in higher order situations. We're going to see how that manifests in the first order situation that we're talking about in these videos, and then ask how we can concisely put all of this together, particularly relying on this idea of the fundamental theorem of calculus. And you're going to see how this concept of the fundamental theorem of calculus is going to allow us to unify everything that we're talking about. Okay, so hopefully we get all of that out in this single video. So just as a reminder, I want to focus for a moment on this very trivial solution or problem, this one right here, where we were working with the differential equation y prime is equal to 3x plus 4. And it was incredibly easy to find the general solution. Here it was, simply through integration. Now, I want to talk a little bit geometrically about what this family of curves here, what it kind of looks like. If we go to Desmos, and I've hopefully got it queued up here, then I can enter in, oh, that means I have to open Desmos on here. Yeah, we can enter in this family of curves. We can literally put 3 halves x squared plus 4x plus c. And we can set up a slider for c to see how these curves vary as we vary this parameter c. And you can see, and I know you know this, but as we move c around, as c gets smaller and smaller, we see this parabola sinking down, 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 right? And if we then turn it around and let c start increasing, we see this parabola going up, 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 up. This is very sensible from, pre-calc days. This is all stuff that you learned because you know that when you add a constant to a function, that translates the graph of that function vertically. If the constant that you're adding is positive, then it translates it upward vertically. And if that constant that you're adding is negative, it translates the graph downward. And indeed, that's what we see happening here as we vary the values of c. Okay? It's always good to have this geometric picture in your mind. And you can see how that value c, it's only after you specify a specific value of c that you see a very concrete graph, right? And that's the passage in going from what we call a general solution, where the c is left unspecified, to a particular solution where you choose a value of c. Now, the way in which that c gets chosen is oftentimes in the form of an additional constraint or specification on the solution. And we call these initial conditions. So let me give you an example of what I mean. So these problems, when you have a differential equation together with a initial condition, these are called initial value problems. This will come up enough that we will abbreviate this IVP, okay, initial value problem. And this is a differential equation. Oh, let me write this in blue. This is a DE together with a particular sort of specification. About solutions y at some value, fixed value, we call it maybe x naught. X naught is very often 0, but it could be other values as well. And so we're sort of saying that y at x naught has to be some value, but we might also be saying things like y prime at x naught has to be some value, y double prime has to be some value, etc. And we have this list of specifications. We call that list the initial values. And what we want to do is figure out a solution which not only satisfies the differential equation, but also meets these additional specifications. So let me give you a very concrete example. Suppose that we're given this same differential equation that we had earlier, y prime equals 3x plus 4. But I further specify that I want that y at, I don't know, 2 is equal to 5. Okay, I'm really just making things up, okay? So this is then an initial value problem. This I would call the DE. This I would call the initial condition. And these things taken together, I would call an initial value problem. Hopefully this terminology all is very sensible. In other words, to solve this now, what I want to do is figure out a solution to the differential equation which further meets this condition here. Now, the way that you typically, or one way that you can go about solving an initial value problem is to first find the general solution. And we've already done this. And just as a reminder, this is y is equal to the integral of 3x plus 4 dx. And oh gosh, I have to do this again. 3 halves x squared plus 4x plus c. Okay, so that's the general solution. And then what we can do, and I'll do it up here just because I have space there, is use the initial condition to figure out what the value of c is. Okay, so use initial condition to find the value of c. How? Well, if we know that y of 2 is 5, then that means that we get 5 when we plug 2 in for x, okay? So we get 5 is equal to y of 2. That's just me writing the initial condition in the other order. And then y of 2 is simply 3 halves times 2 squared plus 4 times 2 plus c. And now this is an 8th grade problem, right? This is something you know how to do. And oh no, I have to do it, I guess. So this is like 6, and that's like 8, and that's c. And this is, remember, 5. So we get the equation 5 is equal to 14 plus c. And we subtract 14 from both sides, and we learn that c is equal to negative 9. Okay? And so, what is the solution to the general, to the initial value problem? Well, it's the particular solution that we get when we put c equal to negative 9. So our solution, maybe I'll call it the particular solution, is y equals 3 halves x squared plus 4x. So all I've done so far is copy the general solution, but now I'm going to replace c by negative 9. Minus 9. And that's the particular solution. Wow, how have I done that? No, and then this, and then and then this. Why doesn't this thing just read my mind already? All right, okay, good. So what is this? This is again, just to emphasize, this is a function which satisfies this differential equation, but which also satisfies this initial condition, the specification that we make for y. Okay. What about this guy? Remember, we had this intractable differential equation, which, y prime is equal to e to the negative x squared. And we wanted to say, well, the general solution was y equals the integral of e to the negative x squared dx. And that's true, okay? But it's not very enlightening. If only because this thing is impossible, right? This is an intractable integral. Nothing that you learned in Calc 2 is going to give you any assistance there. Well, that's just actually not even true. Whatever. Taylor series might help you there. Anyway, moving on. So what if I gave you, though, some kind of initial condition for this? Like, what if I told you that y of 2 is equal to, oh, I did 2 for some reason. Let me change it up. Y of negative 3 is equal to 7, let's say. All right. How could we write down a particular solution using this insight that we've got this definite integral here? Well, to answer that, I want to remind you of something that hopefully you learned in Calculus 1. And this is called the fundamental theorem of calculus, okay? And it's not the fundamental theorem of calculus that you're using almost like on a daily basis. This is the sort of part of the fundamental theorem of calculus which you may have forgotten, but is nonetheless very important. Here it is. So recall the fundamental theorem of calculus, part 1. This is sometimes called part 1. And it says the following. Let me see if I can remember. So if f is merely continuous on the interval from a to b, then we can construct a new function, which we might call big F of x, okay? And this is going to be equal to the integral from a to x of f of t dt. And what's amazing about this construction, which is a weird construction because the input to this function, look at it, this f here, the input goes into the upper bound of integration. But what's amazing about this construction is that this is an antiderivative of small f. Okay, that's the fundamental theorem of calculus, and it's very important and useful. Not only because it's the way in which you prove the other part of the fundamental theorem of calculus, which maybe you do use on a day-to-day basis, but also because of the comments that we're about to make. Oh, I don't like the way it's running up against there. So. Okay, great, lovely, beautiful. Okay, so how is this useful? How can we bring this technology to bear on the previous problem? Well, I just want to make one observation before I answer that question. So observe, for the f above, I want you to notice that f of a is something that we know the value of immediately. Let's think. F of a is the integral from a to a, right, of f of t dt. In other words, an integral where the lower bound is the same as the upper bound. And what must be true about such an integral? It must be 0, right? And yeah, so if we know nothing else, we know that, and that's good. But that's going to help us. That really will help us, right? Because what I can say is, well, this right here is the general solution to this differential equation. And I want to pluck out the one among the infinite from this general solution, which further satisfies the initial condition, namely this. And now, with this fundamental theorem of calculus, I can do that. Observe. So to solve the IVP, and maybe I'll point out the IVP. The IVP that I'm solving here, I'll denote star. Here's star. It's this differential equation together with that initial condition. To solve star, let's write down, let's take y to be the integral. Now I'm going to go from -3 up to x of, again, f of t dt. So e to the negative t squared dt. Okay? Now, I'm not done yet, but just observe, if we plug negative 3 in for x into this integral, we get 0. That's basically this green observation operationalized for this particular problem. Okay? Further, and maybe more importantly, crucially, this is after all an antiderivative of e to the negative x squared. And hence, this, we know, is a solution to this differential equation. This is a solution to this. Why? Because the fundamental theorem of calculus says so. Okay? But it doesn't satisfy, unfortunately, this condition, that y of negative 3 be equal to 7. Because what is y of negative 3 right now as written? It's 0. So what do? Do we curl up in a ball and die? No, it's very simple what we do. We just add 7 to this. Okay? And this satisfies the initial value problem. All right, so we can speak a little bit generally about this, and then I'll finish the video, I promise. To solve in general, y prime equals f of x. So the very particular situation where your general solution just looks like an indefinite integral with initial condition that y of x naught is equal to some number y naught. Okay, y naught's just going to be some fixed number here. We take y equals the integral from x naught up to x of f of t dt. So this is, we know, an antiderivative by the fundamental theorem of calculus, but it doesn't necessarily meet the initial condition, because if we plug x naught into this thing, we get 0. So what do we do to fix it? We simply add y naught to it. This is a complete and total solution, fully general, to the initial value problem in this very specific case where our differential equation is relatively simple. Okay, that's enough for right now. See you in the next one.